Right, so let's do an example for 2D motion. So this will be 2D motion. And what I want to figure out, the question is, how far does the ball travel? So let's look at this at the setup we have here. We have a person here on top of a 23-meter ledge, so pretty high up in a building, and this person decides to kick this ball in this direction. Okay, so he kicks the ball in this direction, and the ball does something like this. Let me draw that better using another color. So this person kicks the ball, and the ball goes like this. Whoop, like that. Okay, so what I want to know is how far the ball goes. So how far it goes here. So basically what we want is this. Okay, so in this problem, we have two types of motion. Remember, 2D motion problems can be broken down into the horizontal motion and the vertical motion. So, since what we want to figure out is how far we traveled in this direction, then we can start looking at our horizontal motion equation. So let's start with the horizontal motion. And we'll be using the horizontal equations. One thing that is very important for us to actually determine at the very beginning of a problem is our plane of reference. Where is our origin going to be? So for this problem, for simplicity, I'm going to place my origin here at the base of my building. And we'll define that in this step. Let me put another brighter color so that we can actually look at it. Uh, so that is my origin. In this direction, I have positive x, and in this direction, I have positive y. Just let me put it again. I was going to tell you to pretend for the lines to be straight, but I can actually make them straight. Okay, so this will be my positive x direction, and this will be my positive y direction. So let's start with my horizontal equations. Remember that delta x is equal to Vox times t. Okay, that is basically it. Delta x is x minus x0 equals Vox times t. X0, so my origin is at 0, and therefore my delta x is simply x. Okay, so my final. Okay, so let's look at the equation we have here. It says that we need both Vox, so we need this value here, and we need time. We can calculate Vox, because, sorry, I forgot to give you this value. So the person kicks the ball with a initial velocity of 8.31 meters per second. Okay, so remember that Vox is equal to the magnitude of my vector times the cosine of the angle the vector forms with the horizontal. But since my velocity vector is strictly horizontal, then theta is equal to 0. Therefore, this becomes Vox is equals to V cosine of 0, which is 1. So we have that Vox is equal to the magnitude of my vector, velocity vector, and this means that Vox is equal to 8.31 meters per second. Okay, so we now have Vox, which will this one is 8.31, but now we need T. T is our value that we don't know. And with this equation, well, we can't get it because this is an unknown and T is an unknown as well. But what we can do is start looking at the problem because the problem is in it's two-part problem. We can look at, let's see, let me choose another color, yellow. We can look at my vertical equations. Uh, in the vertical movement, we do have some acceleration, and this is the value for our acceleration. The sign implies that it goes in this direction because we established the positive y direction to be upwards. Therefore, my acceleration should be negative because it's going downwards. We know that the ball traveled vertically from this point to this point right here. So we know that my initial position of the ball was at 23 meters above ground, above my origin, and my final position of the ball is exactly at my origin, right? It traveled from here all the way to here. So we know that delta y is negative 23. Why? Because this is final y minus initial y, and this is equal to 0 minus 23. It's equal to minus 23. Okay, let me do a new layer. So we already know that y0 equals 23. My final position in y is equal to 0. Therefore, delta y is equal to minus 23. So if we look at our equations, with equation, I believe it's equation number 2, that says this: y equals to 1/2 of my acceleration times my t squared in the y direction plus v o y times t plus y0. So let's analyze this equation, see what we have. We have a in the y direction because we know that ay is equal to minus 9.81 meters per second squared. We don't have t. T is an unknown. Voy, we have it, and this is v sine of theta, but since theta is 0, all of this becomes 0. And that makes sense because it's a strictly horizontal velocity, therefore the y component is 0. Uh, and we have y0, and we have y. We know, therefore, that delta y is equal to 1/2 times negative 9.81 meters per second squared times t squared. Okay, so now this thing, we know that it's negative 23 is equal to minus 4.905 times t squared. This is our only unknown right now. The time it takes for my projectile to fall from 23 to 0, okay, without an initial velocity. This is what this time means. The time of falling, or let's call it time of flight. How much time it spends in the air uh, by falling from 23 meters above ground till 0 meters above ground. So this time of flight, we can calculate it by passing this to the other side, and we figure out that it's 2.17 seconds. Okay? 2.17 seconds. So now we have our total time of flight. Okay? We have our total time of flight, and we know that this is the time that my projectile spends in the air. Now let's look back at our horizontal movement. That we knew that our change in the x position would be equal to our velocity in the x position times a certain interval of time. This time now has become this one. Okay, so it's just a simple matter of substituting. We get 8.31 times 2.17, and we get a total distance of 18 meters. So let's see what I did here. So this is the answer. This is actually the answer to the problem. So that's the horizontal displacement of the ball. But let's look at it from the problem. Okay, let's look at the original drawing. So the first thing that I did was I calculated how much time it takes for this ball to go from this direction, from this position, sorry, till this position. Okay, how much it takes for this ball to actually fall. That time, how much was it? 2.17 seconds it took from this ball to fall from this position to this position is also the same amount of time that it spends in the air. Okay, so it's being accelerated downwards. What's happening? Okay, okay. So it's being accelerated downwards by gravity, and it's taken 2.2 something seconds, 2.17 seconds to actually fall from this position to this position. Those same 2.17 seconds is the amount of time it took the ball to go from this position in the x direction to this position in the x direction. So it's only a matter of plugging in this amount, that amount into, where's the equation? Into this equation. This equation, the only thing that is telling me is the change in time is equal to velocity times time. Okay, change in position is equal to my horizontal velocity times the time it takes to go from one position to the other, to the final position. So that is it. That is why we need to break down this problem into two distinct problems. The only thing, so the only variable that connects both movements is, and I'll put this in huge bright red color, time. So I'll put this in a little bubble. So the only variable that connects these two types of movements, horizontal and vertical, is the time. Okay, it spends the same amount of time falling from here to here at the same amount of time going from this position to this position. Okay, so I hope it's clear. We'll work in class this type of problems a little bit more, and be sure to bring your questions into the classroom. Okay.